Hello, this is the video about metamorphic minerals, part 1 of talking about metamorphic minerals. So just as kind of a reminder about what metamorphic rocks are, so if you've taken Geo 101, you have seen kind of these pictures. So our metamorphic rocks are going to be forming from another rock, and that's going to be via a response to heat or pressure or interaction with fluids. And because of this interaction with heat, pressure, or fluids, the rock is going to undergo a change in texture or a change in mineralogy. And so the pictures we have here on the lower right, I'm showing an example of a change in texture. That's this first set of two minerals here. So we're going from a protolith, so that's our first rock, the original rock before it's metamorphosed. We can see looking at it, it's a granite, it's got potassium feldspar and plagioclase and biotite and quartz. And as it undergoes metamorphism, we're keeping basically the same mineralogy here, but changing the texture. So now we have this kind of foliated, striped appearance to the rock. In contrast, in the bottom here, we have a shale, kind of a mudstone sort of thing, that has formed a garnet schist. And so in this case, we've actually changed the minerals that are present in the rock. So these garnets that were not there before have formed as a result of this metamorphism. And so just kind of putting this in the context of the rock cycle, in the lower left here, we've got our igneous rocks up here. So we've got magma that cools and crystallizes to form igneous rock. That igneous rock might undergo weathering to form sediment, which might then cement and compact to form a sedimentary rock. And then either an igneous rock or a sedimentary rock, or even another metamorphic rock, could undergo some kind of heating or burial process to change the temperature or pressure, turning any of these pre-existing rocks into a metamorphic rock. And so when I'm talking about metamorphic minerals in this presentation and in next week's presentation, I'm going to be talking about new minerals. So these metamorphic minerals are going to be new minerals that are forming as a result of these metamorphic reactions, like the example with the garnet that's forming here from this shale. So metamorphic rocks are going to have a lot of the same minerals, say as igneous rocks. There's going to be quartz, feldspars, micas, but often they're not new metamorphic minerals. They're simply kind of leftover metamorphic minerals, or leftover minerals from the pre-existing rock. That's not to say that there aren't cases where new quartz or new feldspar or new mica can be produced via metamorphic reactions. That does definitely happen. And in that case, those would be referred to as metamorphic quartz or metamorphic feldspar or metamorphic mica. But here we're focusing on the minerals that are new, that really form only in metamorphic rocks, where if you see this mineral in a rock, you can say with a pretty high degree of certainty that you're looking at a metamorphic rock. So the minerals we're going to be talking about in this part are going to be this list here. We're going to talk about garnet. We'll talk about andalusite, sillimanite, kyanite, and why those kind of go along with each other as a little threesome. Staurolite, and then some minerals that are part of groups we've already seen, but this specific mineral member we maybe have not. So we'll be talking about diopside, which is a pyroxene, the tremolite ferroactinolite solid solution, which is a part of the amphibole group, glaucophane, which is another part of the amphibole group, and finally wollastonite, which is what we call a peroxenoid. It's not quite a pyroxene. We'll talk about that later. Okay, so I'm breaking these minerals up into two distinct groups, and these two distinct groups are based on what sort of original rock you would most commonly find these minerals in. So if we're not bringing fluids into our rock, what we have is what we call a closed system. Nothing's coming in or going out of it. And so, for instance, if your initial rock was really rich in aluminum, then if you metamorphose it, you're going to end up with metamorphic minerals that are also rich in aluminum. So this first set of minerals are going to be those aluminum-rich minerals that tend to form from aluminum-rich original rocks, such as mudstone and shale. Then the second group of minerals we'll be talking about are going to be common metamorphic products of calcium-rich rocks, such as limestone, since limestone is made up, as we know, of calcite, of calcium carbonate. So all of these minerals are going to tend to be pretty calcium rich. Okay, so we'll start with those aluminum rich metamorphic minerals. So recall that the main clay mineral that we learned about in the sedimentary mineral section, it was kaolinite, and it had the formula Al2Si2O5OH4. So remember, it was forming as a weathering product from feldspar, which is itself rich in aluminum. So we've kind of taken an igneous mineral, then we weathered it to form a sedimentary mineral, and now we're going to be metamorphosing it to form these metamorphic minerals that are rich in aluminum. And so again, frequently these metamorphic rocks are going to have quartz and feldspar and mica, but we're just focusing on those new minerals that are forming as a result of these metamorphic chemical reactions. So in this section, we'll be talking about garnet, andalusite, sillimanite, and kyanite, and then staurolite. So starting with garnet. Garnet is a silicate. It has the formula X3Y2SiO4 and you'll see that SiO4 written either as it is at the top there with the SiO4 in parentheses, or you'll see it as I've written below in these mineral lists as Si3O12. So those are equivalent. It's just that in the bottom case, we're multiplying that subscript of 3 through to the silica and the oxygen. So that X in the formula is a site for a 2+ cation. So that's going to be taking in magnesium or ferrous iron or manganese or calcium. The Y site then is going to be taking in 3+ cations, so we can get ferric iron, aluminum 3+ or chromium 3+ are the main cations we're going to see in that site. So when I'm trying to kind of remember what the formula for garnet is, I usually try to remember that there are 3 of the 2+ sites and 2 of the 3+ sites. And that adds up to 12, and that's going to cancel out our SiO4 4- that we have 3 of. And so within the garnets, we break them down into 2 different groups. They have dumb names, I think, the 2 groups. One of them is called the pyrrolspite group. Those are going to be our aluminum-rich garnets. And then we're going to have the eugrandite group, the calcium-rich garnets. So to some degree, I could talk only about the aluminum-rich garnets now and leave the calcium-rich garnets to the calcium-rich minerals that we're going to talk about in a minute here. But breaking the garnets up into 2 different parts didn't seem to make much sense to me. So I'll be talking about both the garnets here. So these names are just the names of the individual minerals in the group kind of smushed together. So the pi from pyrope, the al from almandine, and the sp from spessartine. Then we've got the eugrandite group, we've got the U from uvarovite, the gr from grossular, and the and from andradite. So that's where those group names come from. So for the aluminum garnets, we've got 3 of them. We're varying that X the 2+ cation, so pyrope is going to be our magnesium aluminum garnet, almandine is going to be our iron aluminum garnet, and spessartine is going to be our manganese aluminum garnet. And of course, as you might imagine, there's solid solution between all three of these. In the eugrandite group, we have calcium now as our X component for all of them, and our Y can vary between aluminum, so grossular is going to be our calcium aluminum garnet, andradite is going to be our calcium iron garnet, and uvarovite is going to be a calcium chromium garnet. So, showing some examples of these garnets on the right here, you'll see they come in kind of several different colors, mostly red and dark red, but sometimes yellow or green, and we'll talk about which of these different minerals can take on those different colors. But first, I wanted to talk a little bit about the crystallography of garnet. Everybody loves symmetry and crystallography. So garnet falls into the isometric crystal system. So remember, that's the kind of the first of our crystal systems with the most symmetry, where all the axes are equal in length. So we have an A1, A2, and A3 axes that are all at right angles to one another. And so as a result of that, the crystals of garnet themselves are going to tend to be equant rather than elongated. So they're going to tend to have kind of equal dimensions in all dimensions. So some of the frequent habits that you see for garnet are going to be dodecahedra. So here's an example of that. This is a rhombic dodecahedron. So dodecahedron, meaning that it has 12 faces. Rhombic, meaning that each face is a rhombus. Over here, we've got a trapezohedron. You can see that each face is a kite sort of shape. And so you'll frequently see, if you have a fairly euhedral garnet, these are some of the shapes you'll see. Down here are some cool examples I found of modified trapezohedra and dodecahedra. So again, by kind of combining a whole bunch of different crystal forms, you can get shapes that kind of start off as a trapezohedron, but have the corners cut off a little, or something that starts out as a rhombic dodecahedron, but has the edges cut off a little. So euhedral garnets are going to look something like kind of one of these examples. You can also get kind of massive, or if you have very small garnets that have weathered a bunch on the outside, they can tend to granular habits as well. And so you may have noticed from the formula for garnet, we have this SiO4 in parentheses. That's one of the benefits of writing the 3 outside the parentheses, is that it allows us to see what our silicate group here is. And so because we have that SiO4, just the same way we have SiO4 in olivine, so our olivine formula, remembers Mg2SiO4, so that SiO4 is indicating that we have a nesosilicate, where we have these isolated tetrahedra. So we're looking at a relatively silica-poor mineral here. We have 4 oxygens for each silica, none of them are shared. And so like olivine, and because of this isolated tetrahedra pattern, garnet also has no cleavage. It tends to fracture. It has a high hardness, and between its high hardness and its really pretty colors, that makes it a common gemstone. And also because of its high hardness, it's used in place of quartz as an abrasive sometimes. So just one more kind of discussion about the shape of garnet. Yeah, see, you get like all these Steven Universe things if you search garnet. So again, we're looking at an isometric crystal here. The color on this is kind of messed up. I would not believe the colors that you're looking at here, but this is a really nice example of that rhombic dodecahedron shape. And so I just wanted to kind of relate this back to the symmetry lessons that we did right before spring break. So if we're in this isometric crystal system, then what we're expecting to see when we look at this crystal is some axes of fourfold symmetry, some axes of threefold symmetry, and some axes of twofold symmetry. So remember that that was kind of what defined our cubic crystal structure. So if we rotate this crystal around, so here's a nice example of a fourfold symmetry. You can see that cross pattern where you could rotate by 90 degrees. You'd come back to the same shape you had before. We rotate it around a little bit more. We can find threefold symmetry. So now rather than having a cross with four kind of spikes coming out of it, we've got a threefold thing. So now we can rotate by 120 to come back to where we were before. And then finally, we're going to be looking for some twofold symmetry. And so here is an example of twofold symmetry. So if I rotate around this middle point here, we would have to bring this line around 180 degrees before the shape had the same shape as before. So that's an indication that indeed this is an isometric crystal that we're looking at. All right, so moving on to the color of garnet. So garnet can take on a wide range of colors, but it's relatively specific to the type of garnet. So the red, maroon, purple, brown garnets that I think is probably what most people think of when they hear garnet and they think about the color of garnet. That's going to be primarily our pyrope and our almandine. So that's going to be our magnesium and iron-rich aluminum garnets. Spessartine is going to be kind of an orange color. It's kind of orange, almost candy, like fake orange flavored candy color here. And then andradite is going to be kind of yellow to yellow-orange to green. So we've got a kind of orangish andradite crystal here in the middle, or cluster of crystals. We've got a yellow andradite crystal down in the bottom right, and a green andradite crystal down here in the bottom middle. And then uvarovite is going to basically always be green, this very bright kind of apple green. So here's some examples of uvarovite. Again, you can see that rhombus shape, so these would probably also be rhombic dodecahedra. Here's a nice view looking down one of the threefold axes, and a nice view here looking down one of the twofold axes. In the case of spessartine, that's our trapezohedron. We can see the kite shape really nicely here, but here we're looking down one of the fourfold axes. So even though the faces between this rhombic dodecahedron and this trapezohedron are different shapes, both of these crystals are going to have the same symmetry contents. And this is a visual that I really like, showing kind of the end members of these garnet solid solutions, and showing that indeed there's all of these are connected. So as we would expect, given how easily magnesium and iron can substitute for one another, we have full solid solution between almandine and pyrope. So we have our kind of red and orange garnets here as our aluminum-rich garnets, and then we've got our green and yellow and kind of gold-colored garnets here as our calcium-rich garnets. And grossular, because it has both calcium and aluminum, is kind of intermediate between these groups. And so grossular comes in the widest range of colors. It can take on kind of an orangish red color or a yellow or green color. So that's garnet. Super pretty. Okay, so moving on to andalusite, sillimanite, kyanite. These are three polymorphs of the same mineral formula. So remember, polymorphs, we've got multiple shapes from the same elements. So all three of these have the chemical formula Al2SiO5. So these are silicates we're looking at here. But even though they have the same mineral formula, they look very different in hand sample. So going through each one of those, so andalusite is orthorhombic in its symmetry. It's going to tend to be prismatic to massive, and it's going to usually have this kind of this reddish brown color to it, though it can also tend to a tan or white or gray color, as we can see in the bottom left and bottom right here. So in the case of the bottom left, there's actually graphite that's come in as this crystal was forming. That's what makes these really interesting cross shapes. Andalusite is also very hard, so it has a hardness of 7.5 on the Mohs hardness scale. So if we're looking at this mineral, probably the mineral you'd most easily confuse it for would be one of those kind of reddish or reddish-brown garnets. And so that's, again, where the habit and crystal symmetry group is going to be very helpful, because once you see something that's kind of elongated and prismatic, like this crystal in the upper right, you know that you're looking at something that's more orthorhombic than isometric. Sillimanite is also orthorhombic, but it's going to have a fairly different habit. It's going to range from kind of acicular to fibrous, so you're going to have these very long, slender crystals. The color is going to usually be white, though it can range from tan to gray to pale green. It's not quite as vitreous as andalusite, or as we'll see kyanite is, so we call it kind of subvitreous. It's like kind of glassy in some cases, but it can also range to greasy or silky. So I think this example in the bottom middle here is a really good example of kind of a greasy texture for sillimanite. It also has one-dimensional cleavage, so that's also going to help distinguish it from some of these other minerals. And it's also hard, although less hard overall than andalusite. So same mineral formula, but very different looking in hand sample. And kyanite. Kyanite is one of the best minerals. It's so pretty. So kyanite, unlike the other two polymorphs of Al2SiO5, is triclinic, so it's not orthorhombic, it's triclinic, so it has less symmetry. And its habit is, in general, going to be bladed. You see these very nice, beautiful blue blades of kyanite in all of these samples here. The color is super diagnostic, this blue kind of gray silver color. So between the bladed habit and that blue color, kyanite is one of those minerals that's usually pretty easy to identify. It also has 1D cleavage, so you could kind of imagine cutting down from the top of these blades. That would be the cleavage plane there. And just as kind of an interesting side note, kyanite's interesting in that it has two different hardnesses depending on the direction. So if you try to scratch it in one direction, it's going to have a hardness of 5. But if you try to scratch it in the other direction, it's going to have a hardness of 7. So that's kind of weird and interesting. And will actually relate in a little bit to what we'll be talking about in the plane polarized microscope lecture this week, where we'll be talking about the different properties that minerals can have when you look at them in different directions. So the stability of andalusite versus sillimanite versus kyanite, so in other words, if you got a huge blob of Al2SiO5, which mineral is actually going to occur is going to be determined by pressure and temperature. So we've got a phase diagram on the right here. We've got temperature on the x-axis increasing to the right, and then pressure on the y-axis increasing downwards. So that's simulating depth in the earth, so that you can kind of imagine if you're a little person standing on the surface, as you go deeper and deeper and deeper into the earth, you're going to get to these deeper stability fields. And so what we see here is that sillimanite is the high temperature polymorph of Al2SiO5. It exists only at high temperatures. That, again, if you've had Geo 101, that's going to be the highest grade of the three minerals because it's going to be at the highest temperatures and pressures. Kyanite exists at low temperatures. So you'll never find kyanite in a rock that's been heated to more than about 700 degrees Celsius. And then andalusite exists in this kind of middle temperature range and low pressures. And so of these minerals, kyanite's probably going to be the most common overall, just because it's the one that exists at conditions closest to surface conditions, so low temperatures and low pressures. And so this is really, really helpful when it comes to identifying kind of what conditions metamorphic rocks have undergone, because if you find sillimanite in your rock, you automatically know that it's been heated to high pressures. If you find andalusite in your rock, you automatically know that it hasn't gone to terribly high pressures. Okay, so the last of our aluminum-rich minerals. Look at all that aluminum. 18 aluminum, also 48 oxygen. So this is a very wonky formula. We have an H group at the end instead of an OH group like we're used to seeing. So this is a silicate, but it's not going to fit into kind of the nice silicate categories that we've already defined. Staurolite is monoclinic. Gets called pseudo-orthorhombic, so I think there's a question about this in the reading. So monoclinic, you're going to have an angle that is not at 90 degrees from the other axes, but it's very, very close to 90 degrees. And so if you just look at the crystal, it's going to look orthorhombic, even though it is technically just barely monoclinic. So it's going to form these kind of blocky, prismatic, euhedral to subhedral crystals. It also frequently forms what are called cruciform twins. So examples of those are shown in these basically everything on the right side here. So cruciform means cross-like. So you can see how the crystals form these cross-like structures. And so that word twin basically means that the mineral grew in two different directions. So we've got one crystal that grew out from an initial nucleation site such that its C-axis, its elongated axis, is aligned this way, while another crystal formed out of that same middle nucleation site with a C-axis this way. So we'll be talking about twinning a fair amount in the petrographic microscope portion, but this is a really nice example of twinning in hand sample. So staurolite is pretty diagnostic based on its color. It's a reddish brown to brownish black in color. It's also pretty diagnostic based on its luster, so it frequently has a more dull luster than a lot of other silicates. So it can be vitreous. This is a beautiful example of some vitreous staurolite here. And then we've got maybe some kind of resinous staurolite here. We've got a cute little garnet here at the top, adorable, probably almandine or pyrope based on that color. That makes sense since those are the two main aluminum-rich garnets. It makes sense that we would see them in conjunction with staurolite, which is also an aluminum-rich mineral. But more frequently, staurolite is going to be pretty dull looking, so examples like this, or certainly this, or these in the bottom right are examples of some of the kind of very dull looking staurolite that you might find. Okay, so moving on to calcium-rich metamorphic minerals. So these are going to be forming primarily during the metamorphism of calcium-rich rocks. One good example of which is going to be a calcite-rich rock. So limestone is made entirely of calcite. And so if you're metamorphosing calcite into the metamorphic rock marble, if you have any kind of impurities bringing other elements into that system, you can form a lot of other interesting minerals. So we'll be looking at diopside, tremolite and ferroactinolite, glaucophane and vlastenite. All right, so diopside, CaMgSi2O6. That Si2O6, the ratio of 3 oxygen to 1 silicon, should clue you in that we're looking at a pyroxene. We've got a bunch of calcium in this pyroxene. Because calcium's very large, it distorts the structure, so that's going to force us into a clinopyroxene structure. So we're going to have a monoclinic rather than orthorhombic crystal system. So in the bottom right here is a reminder of the pyroxene quadrilateral. So when we were looking at igneous minerals, we were primarily looking at augite as our clinopyroxene, or enstatite as our orthopyroxene. Now we're up here, we're a little more calcium rich, looking at diopside as our metamorphic pyroxene. And so the color of diopside is going to range from green to white, usually green to pale green. Like most pyroxenes, it's going to be pretty blocky to prismatic. It's going to have the usual pyroxene cleavage, 2 directions at nearly 90 degrees. You can see that nicely in this crystal here. So it kind of follows all of the normal rules of pyroxene that we're used to, but now is showing up in a metamorphic rock. Okay, so tremolite ferroactinolite, kind of the amphibole equivalent of diopside. So it's got this site X5 that can take in a 2+ cation, so that's going to be iron 2+ or magnesium 2+. So we have a calcium-rich amphibole that can take in either iron or magnesium. So the tremolite end member of this solid solution is going to be the magnesium end member, so Ca2Mg5 Si8O22. Again, that's that pyroxene group that we're used to seeing, OH2. And then ferro, that ferro at the beginning there means we're looking at something iron rich. So this is going to be our iron end member, Ca2Fe5 Si8O22OH2. So that Si8O22, again, tells you we're looking at an amphibole. So we're looking at a double chain silicate. And just like in the case of diopside, we're looking at kind of green to white crystals here. But of course, like most amphiboles, we're looking at a much more bladed habit rather than that blocky prismatic habit that we saw in the case of diopside. So amphibole ternaries are much more complicated than just a triangle or a quadrilateral, because they have a whole bunch of different places that elements can substitute into. So remember, there's a site here that is unoccupied that could have sodium or potassium filling it up. And so this is just kind of a subset of some of the amphiboles, thinking about the compositions of some of the amphiboles. And so here we're just varying, we're keeping that Si8O22OH2 constant, but we have calcium going up to an unseen point here, magnesium at this end member of the ternary, and iron at this end member of the ternary. And so this tremolite ferroactinolite is going to be part way up that magnesium to calcium line, specifically 2/7 of the way up that line, and is going to kind of bridge this middle ground here. And then there are other amphibole solids solution series, such as the Cummingtonite Grunerite series or the anthophyllite, that fill in these other gaps. And so just as a reminder, when we were looking at igneous amphiboles, we were talking mostly about hornblende. Hornblende did have some of that initial cation site for sodium and potassium filled in, and then had this Ca2 whole bunch of stuff amphibole formula. And hornblende is always going to have a fair amount of aluminum, which note that our tremolite ferroactinolite series and our anthophyllite and our cummingtonite grunerite, none of these are aluminum rich amphiboles. So these are our calcium rich amphiboles up here. Then these are our just magnesium iron rich amphiboles down here. But we would need a third dimension to represent the amount of aluminum in amphiboles as well, if we wanted to represent kind of the whole range that amphiboles could take. And in fact, we'd actually need like a fourth dimension or even a fifth dimension to represent this amount of sodium and potassium as well. So amphiboles are very complicated and a little bit harder to kind of draw out on paper in terms of their solid solutions. A good example of that is glaucophane. So glaucophane is also an amphibole, so it's going to have the same double chain silicate structure. So we see our Si8O22OH2 here. But now we have sodium instead of calcium. So if we go back here, we had Ca2 and then iron or magnesium 5. If we come here, we have sodium 2 and then a combination of magnesium and aluminum adding up to that 5. So because we're adding extra charge in with the aluminum, we're adding 2 extra charge for those 2 aluminum. We need 2 fewer charge over here, and so that's what allows sodium to sub for calcium in this spot. So this mineral, main identifying factor is that it is very blue. So it's blue to dark blue to black. It's going to be kind of acicular to fibrous to massive. It generally does not form very pretty crystals, though I have included a couple examples of what it looks like when it does feel like being pretty. And we'll be talking in the petrographic microscope section this week when we're talking about plane polarized light, that one of the diagnostic properties of glaucophane in thin section is that it is pleochroic. It's going to have a different color under the microscope depending on which crystallographic axis you're looking at. So as you rotate glaucophane on the microscope stage, you're going to see it go from blue to more colorless to blue to more colorless. I also included this picture in the lower right here of what is almost certainly Catalina Island. Catalina Island is kind of the mecca of metamorphic rocks if you're on the west coast, or really if you're in most places. Just beautiful, beautiful metamorphic rocks. I went there for a field trip for my metamorphic petrology class in undergrad. We went snorkeling. It was a lot of fun. But you can see just how blue this rock is. And so as soon as you see a rock that's as blue as that, you're going to guess that it's pretty rich in glaucophane. And so because these minerals are rock type called schist, when we see this color, we're going to be calling that a blue schist. Whereas if we saw a rock that was more rich, going back a second here, in tremolite and ferroactinolite, we saw a schist that was rich in these minerals, we would call that a green schist. So even just by looking at the color of the rock, we're able to learn something about what minerals are present. And just like with the kyanite, sillimanite, andalusite example, that's going to tell us something about the conditions of formation of the rock. All right, so our last mineral for this session is wollastonite. It has CaSiO3. So when you see that SiO3, you should immediately jump to that being a pyroxene. But turns out wollastonite, a little weird, it is actually a peroxenoid. So That means that it is pyroxene-like, but not exactly a pyroxene. And so recall that calcium is going to be a larger ion than magnesium and iron. And it's that larger ion that makes clinopyroxene of a monoclinic structure rather than an orthorhombic structure. You're kind of distorting the octahedral sites to allow that calcium in. But you can only do so much of that and actually retain your pyroxene structure. You can only go up to about 50% calcium in those octahedral sites if you look at the pyroxene quadrilateral down in the lower left here. Once you get more calcium rich than that, you're actually going to distort the structure of the pyroxene chains, those single chains of silica tetrahedra. And so it's still going to be a single chain silicate, and it has the formula of a single chain silicate, but the chains are going to kink ever so slightly in order to allow that larger ion into the structure. And so those kinks mean that it doesn't have a strictly pyroxene structure, and so we call it a peroxenoid instead. So wollastonite, it's going to usually be kind of massive, blocky, bladed, acicular, so usually going to be these fairly thin crystals. They're going to be colorless, white, gray, and the cleavage, again, like pyroxenes, it's going to be about 90 degrees, but interestingly, it's actually slightly less like 90 degrees than other pyroxenes. So probably wollastonite, the mineral you'd most easily confuse it with, would be sillimanite, because they both have these fairly slender white crystals. And so this is kind of where having a knowledge of other minerals in rocks is going to be helpful. So sillimanite was one of our aluminum-rich minerals. Wollastonite's one of our calcium-rich minerals. And so if you were trying to identify and distinguish between these two minerals, you might look at what other minerals existed in the rock. So if you're seeing a lot of tremolite and diopside in your rock, then you're probably looking at wollastonite because you're metamorphosing a calcium-rich rock. If instead you see staurolite and garnet, you're probably instead looking at sillimanite because you're looking at an aluminum-rich metamorphic rock. So just to summarize this part, we had these two groups of minerals. We had the aluminous minerals and the calcium-rich minerals. So the aluminum-rich minerals, we had the garnets that we could divide into two main series, the calcium garnets, which are going to tend to be kind of yellow to green, and the aluminum garnets, which are going to tend to be kind of red to brown to purple. Then we had our three polymorphs of Al2, SiO5, sillimanite, kyanite, and andalusite, which can be very useful, as I said, for determining those pressure temperature conditions that a metamorphic rock underwent. Then staurolite, which is going to be dark brown, kind of dull habit, and frequently twinned. Then for our calcium-rich minerals, these are mostly members of mineral groups we've already learned about. So we had diopside, which was our calcium-rich kind of green clinopyroxene. Tremolite ferroactinolite, which is our calcium-rich green amphiboles. Glaucophane, which is actually sodium-rich rather than calcium-rich, but shows up in similar rocks. So this is our blue amphibole that gives blue schist its lovely color. And then wollastonite, which is a calcium-rich white peroxenoid, similar but not quite a pyroxene. So thanks for joining in for learning about these metamorphic minerals, and I will be back next week with more metamorphic minerals, and back later in the week with a video about properties of minerals in plane polarized light.